All right, so the big ideas before we jump into topic three. What is relative dating? What is the law of superposition? Which strata, which is another word for layers, are older, the lower ones or the higher ones? Okay. If an intrusion or fault goes through a stratum, again, just another word for layer, is it older or younger than the layer? What is an index fossil? To continue to talk about fossils a bit, and how do index fossils improve the precision of our relative dating? So as you may have been able to tell from the big ideas that you want to be able to pull out of this topic, okay, we are looking now at, great, we've got all this evidence of the Earth's history, we look at all this stuff, how do we actually start to order it? How do we actually start to say, okay, this thing happened before or after this thing, and start to put it together into a timeline? Today in topic three, we're going to be looking at relative dating, okay? So relative means related to something else, right? You are related to your relatives. So this doesn't necessarily provide an actual age for whatever geologic evidence it is we're looking at, whether it's fossils or cracks, whatever it might be. But it does allow us to see where it fits in relative to other pieces of evidence. Okay, so for example, it's older than blank, but younger than blank, right? So for example, if I say you are younger than me, but older than a baby, right? Do I actually know how old you are? No, but I am kind of giving a range, right? There is a relative date. I haven't said you are 17 years old, right? But I've said that you're younger than me, you're older than a baby, kind of given a rough estimate, right? A stranger has no idea how old you are when I say that, but they know you're younger than me and they know you're older than a baby. Okay, so if I said you were 17 years old, that gives an actual estimate. That would be absolute dating. Okay, so we'll do that in the next topic, but absolute dating gives us an actual estimate of the age in years. So, for example, absolute dating would be, for example, okay, so for relative dating, the one we're doing today, you need to compare to something else. It's how old this evidence is relative to something else. So it's where it fits in. It's not necessarily how old it actually is. Okay, so in relative dating, it all relies on something fundamental to geology, and that is the law of superposition. Okay, super just means above, position just means position. Okay, so the law of superposition goes like this. So to imagine where the law of superposition comes from, I want you to think about your laundry basket. Okay, so you wear a t-shirt on Monday, and then you go home and you put it in the laundry basket. Okay, then on Tuesday, you go to school, you wear a t shirt, and you come home after Tuesday and you put it in the laundry basket. On Wednesday, you do the same thing. Get home, put your shirt in the laundry basket. Thursday, Friday, same thing. Question for you: which shirt is on top of your laundry basket? Well, it should be your Friday shirt, right? The one you wore the most recently because you took it off and your Monday to Thursday shirts were already in the laundry basket, and in goes your Friday shirt on top. Which shirt is on the bottom of the basket? That's right, your Monday shirt, right? You wore it first, so it went in the basket first, so now it's on the very bottom underneath the Tuesday to Friday shirts, okay? That's how rock layers form too. So there's a layer there, and then other sediments get kind of deposited on top over time. So you can't ever have a younger layer below an older layer, right? How did the older layer get above the younger layer? That wouldn't work that way. Your Monday shirt isn't going to just magically appear above your Friday shirt. Now they can kind of shift, but they're still going to stay nicely in their layers. Okay. So the law of superposition is younger layers are always on top of older layers. Okay. That's the main idea behind it, but there's another very important idea here. Okay. Now I want you to kind of go back to your laundry basket and imagine your little sibling comes in and they spill grape juice all over your laundry basket. Okay, so all of your shirts, Monday to Thursday, they get a little bit of grape juice on it. You can look at them and see little purple specks. Okay, but the grape juice dries. Okay, so those ones have grape juice on them. Okay, but the shirt you wear the next day, now that the grape juice is dry, when you put it in there, is it going to have that grape juice on it? No, right? Because the grape juice event, your little sibling spilling grape juice, happened before that new shirt layer got formed. So that's kind of this second layer. So faults, remember faults from when we were talking about earthquakes, it's essentially just a crack in the lithosphere, right? So a fault, a crack in the lithosphere, usually caused by plate tectonics or intrusions, which are basically just it's magma that has worked its way into a layer and cooled and hardened into rock. So it's just kind of a almost like magma leaking into a layer, they have to be younger than the layers they cut into. So the layers that they go into. So if a fault cracks through a layer, well, that layer already had to be there when the fault formed. So the fault must be younger than that layer. Just like the grape juice event is younger than all the shirts that it stained. The shirts were already in the basket. Your sibling came, spilt grape juice, and that event is more recent. If you put another shirt in there, now that shirt is younger than the grape juice, and so it doesn't get that stain on it, right? So these events, these faults and intrusions that happen to layers must be younger than the layers themselves, okay? Important term here, stratum is just a layer of rock, okay? And if we have more than one, we call it strata. So we're actually just gonna get a bunch of practice here applying the law of superposition. This is a huge part of what geologists do. It's called stratigraphic sequencing. So strata, layers, graphing kind of means mapping it out, right? Looking at it, and sequencing means putting it in order. So we're going to just practice that. So it's asking us here, which letter out of all the labeled letters represents the most recent event? Okay, so remember, law of superposition. Younger layers are on top of older layers, and any intrusions or faults are younger than the layers they cut into. Okay, so you can see the layers here, right? A is a layer. There's this layer that's not actually labeled, but that's another layer. Then there's a layer below that and a layer below that, and so on and so forth, okay? Now, the first part of the law of superposition would make us at first think that A is the most recent layer, right? A is the youngest. That's the shirt on top of the basket. But notice something. See what B is? Okay, looking at B here, okay? B is an intrusion. And notice, yes, A is the youngest of the layers, but B is even younger than A, because how could B have done this? How could B have cut into A if A wasn't already there, right? You can't cut into something that didn't already exist. So A must be actually older than B. A would be the youngest, but B cuts into it, so B is even younger than A. So the most recent geologic event, B. Okay, so if A hadn't already existed, there would be no way for B to have intruded into it, to cut into it. All right, law of superposition. So this example wants us to arrange 3, 6, 2, 4, and B in the correct order from oldest to youngest. So we're going to go from oldest to youngest on 3, 6, 2, 4, and B. Okay, so I've just gone ahead and color coded these just so they pop out a bit more, okay? So let's just kind of start. Let's see if we can find the youngest of the ones we're looking at. So right away, my eye goes to the fact that, look at this, blue, 3, right? 3 being blue, goes all the way to the top, right? And so think about this layer here. This would be the youngest layer. Okay, this is kind of like the youngest layer, but what is the word for 3 again? What type of geological feature is 3? It's an intrusion. See how you can kind of see how magma would have bubbled and oozed and seeped its way into these layers, right? Well, for it to have done that, those layers needed to already exist. So, law of superposition, intrusions are younger than any layer they cut into. And this 3 here cuts into even the youngest layer. So 3 is younger than the youngest layer, right? So no question about it, 3 has to be the youngest thing here, okay, in the whole picture. So 3. Now let's kind of work our way down. I look at 6 and I think, 6 looks pretty young, right? 6 is definitely the next lowest thing. Let's just be careful. Does anything cut into 6? Okay, so 6 is definitely younger than 2. It's on top of 2. It's definitely younger than 4. It's on top of 4. Just be careful here. Look at B. We're safe, but notice that if B did crack through 6, B is a fault, right? It's a crack in the lithosphere. If B did cut through 6, B would be younger than 6, but we're safe. It doesn't, right? So this crack happened sometime, and then 6 formed. Some layer formed on top of all that cracked stuff. So after 3, I would definitely say 6. Okay, now things are going to get a little more interesting. Let's look at 2, 4, and B. So first things first, let's look at B. Does B cut through 4 and 2? You bet. You bet, right? Whoops, I forgot this little piece of 4. See how it's the same pattern? That's also 4 there, okay? So yeah, B cuts through 4 and 2, right? So right away, okay, 4 and 2 we can look at in a sec, but notice how could B have cracked 2 and cracked 4 if 2 and 4 didn't already exist, right? Crack something that doesn't exist. Go ahead, do it. You can't, because you need it to exist to crack it, right? So B must be younger than 4 and 2. 4 and 2 already existed, and then B came along and cracked it. B, by the way, is the fault, a crack in the lithosphere. So now it comes down to 2 and 4 for which one of those is the oldest. I wouldn't blame you for thinking that 4 is younger. I wouldn't blame you, okay, because it does look like it's above it. But notice, is 2 a layer, right? See how these layers are nice little stacks? No, right? 2 is not a layer. 2 is intruding. It's like bubbling magma. Just like 3, 2 is a intrusion, right? Notice it's not a nice layer. It's kind of like a magma leak that's gone into other layers, hardened and formed rock. And sure enough, it's leaked and hardened into layer 4. So layer 4 must have already been there when 2 started intruding into it, right? You can't intrude into a house that doesn't exist. So since 4 already existed when 2 was born, whoops, and I'm realizing I did these, whoops, I just realized I did these backwards. The question said oldest to youngest. I've been doing youngest to oldest. Sorry. Okay, I'm going to change that to youngest to oldest. Sorry if you were confused reading that. Okay, so since 4 already existed when 2 was born, 4 must be older than 2. So 2 is the next youngest, right? And then B cracked it. But before 2 intruded into it, 4 had already existed. Okay, this one just asks us to find the fault. This is kind of fun. It's like an I Spy. Do you see a fault anywhere here? So remember, what's a fault? It's just a crack in the lithosphere, right? Now, when there's a crack in the lithosphere, remember, the plates move, right? So there's kind of a sliding. So that means on both sides of a fault, it won't really match up, okay? So I know you kind of see these lines. However, notice that the layers match up really well. That's probably not a fault. This is probably just kind of layers within the rock. Notice here, though, see this big crack? And nothing on either side of it really matches up. So it looks like there were some layers that used to look nice, and then there was probably a huge earthquake kind of led to this slipping of the Earth's crust, a fault, okay, a fault line. So there is our fault, okay? Now it's asking us which came first, G or D. Let's just highlight G and D so we can see what they're talking about. So there's G, okay, and D's right here. Okay, so I've highlighted the layers here that are relevant for part B here, okay? So I've done the kind of first thing for you. I do really recommend pause the video, try this one on your own, okay? See if you can get to the answer. And then if you're stuck or you want more explanation, you can come back and listen to my explanation, okay? But try this on your own. You can do it. Now, what do you think came first, G or D? Well, remember, intrusions are younger than any layer they cut into. So let's look at what layers G must be younger than, okay? Well, G cuts into this whole H layer right here, right? This whole kind of trying this layer here. D doesn't. So G must be younger than this whole thing, right? It looks like when D formed, this was probably the surface of the Earth. D is an intrusion, so magma is bubbling up, and then it hits the surface of the Earth and it kind of just spreads out and cools, right? There's no more layers. There were no more layers for it to intrude at the time it formed. Whereas when D was finished forming, millions of years later, H came along and formed this whole layer here, right? And then a few million years after that, G intruded into that. So when I look at this, I say G must definitely be younger than D because G intrudes into a layer that is younger than D. G is younger, D is older. So D came first because okay, so H must be younger than D because D didn't intrude into H. So H probably didn't exist when D formed, but G does intrude into H. So if G is younger than H and H is younger than D, then obviously G is younger than D, right? It's like if you have 3 siblings and you're the oldest, H is the middle sibling here and G is the youngest sibling. You would be D. Okay, again, try these on your own, especially C, okay? Since C is kind of the new thing we're learning, see if you can answer part C here, which asks, if the fault is older or younger than A, okay? Then if you want, come back to the video, press play or skip ahead and see if, and check if my answer matches yours. All right, let's start with A. Why might the strata be curved? So remember, strata just means layers, right? So notice how they're kind of wavy like this, right? They kind of have this wave to them. Does that look like something we might have seen a diagram of before? I don't blame you if you don't remember. It was a while ago, but remember when we were looking at earthquakes And you can imagine, right? If these are kind of getting pushed up against each other, or they used to be anyway, they would kind of start to crumple and a lot of pressure would build up. Remember the rulers, right? The rulers started to bend under all the potential energy. That's even more supported by the fact that there's this crack here, right? This fault. When do we get a fault? When that potential energy builds up and cracks and breaks and releases in a fault and sends out seismic waves, earthquakes, right? So I'm thinking probably they're probably curved from stored potential energy built up. They're kind of getting scrunched up from tectonic plate motion. And now part B asks about A. How might A have occurred? First of all, what is A? That's right. That is an intrusion, right? Notice how it's like a layer of rock that kind of intrudes into the other ones, right? It kind of barges through them. So this is some magma that's worked its way, kind of seeped its way into other layers of rock, bubbled up from below, okay, and then hardened into a new kind of quote unquote layer. So A is definitely an intrusion. All right, so A is an intrusion. Magma has kind of bubbled up from below and then eventually cooled and hardened into rock. All right, now can we identify a fault? That's part one of C. Do you guys see a fault? Remember, a fault is a crack in the lithosphere, and on either side of a fault, the layers don't quite match up anymore like they used to. Uh-huh, sticks out like a sore thumb, right? Look at that. Notice how it almost looks like this one has kind of slipped down that way. That is what happens during an earthquake, right? Again, these two plates get pushed towards each other, pushed towards each other. That's why they're getting scrunched up, like pushing those two rulers together, like we saw during earthquakes, right? And then when all that pressure breaks, crack, and one kind of slips down, right? So you can see these polka dots used to be up here with these polka dots, or these bigger polka dots used to be up here with these bigger polka dots, right? But they've kind of, this plate has clearly kind of slid down during that seismic activity that's happened. Okay, now it asks us, so can you identify where a fault is? Yes, a fault is definitely B. And now it's asking us, is the fault older or younger than A? Huh. So A we said was an intrusion, B is a fault. What do you think? Is A younger or older than B? Which one was there first? Well, if A was there first, then when B came along and cracked it, A would have got cracked too. So A can't have been there first. On the other hand, if B was there first when that crack happened, A would have come along the intrusion and kind of filled it in and hardened, right? So which one of those things looked like it happened? Did A kind of fill in B or did B crack through A? Yeah, right? A filled in B. So this fault happened, right? This earthquake happened where this energy was released. There was a crack, okay, sat like that for millions of years, and then some magma came in and intruded and hardened over the crack too. So the fault is older than A. So you could think of it as because A intruded over the fault, or you could think of it as because the fault didn't crack through A, right? Same potato, right? Because A filled in B, or because B didn't crack through A. Those are both good reasons for why A must be younger. Obviously, B was already there when A formed. So I just want to remind you, this law of superposition, what have we been doing? Have we ever said that A is this many years old? Have we ever said that B is this many years old? No, right? All we've been able to say is that A is younger than B, right? But we don't know how old A is. We don't know how old B is. We're doing relative dating, right? As soon as you're comparing something to something else, that's relative dating. We can't say A is blank years old. We can just say it's younger than B. Something that can kind of let us fine tune our relative dating, where we can make it a little more precise than it was with the just saying, well, it's older than this layer. I don't know how old this layer is, but it's younger than that one. Okay, is using something called index fossils. So index fossils are types of fossils from organisms that meet these four criteria. Okay, so they need to be easily recognizable. You can't wonder what you're looking at when you look at it. They need to be common. There needs to be a lot of them. Otherwise, they won't be very good for comparing, right? If only 3 of these exist, they're not going to be very good for comparing. They have to have lived in a large area so that you can find them in one area and then find them in another area and be able to correlate between those two areas. And a really big one actually is that they need to exist for a pretty short time. And when we say short time in the history of the Earth, we mean like a few million years or so. Okay, they need to have gone extinct pretty quickly after they appeared. This is maybe the most important one, right? Because it gives a rough range of the age of the layer we found it in, right? So, for example, if we find some fossil that we know only lived for about 1 million years, well, boom, right away, now we know that whole layer is from that 1 million years, right? Somewhere in that 1 million years. We still don't know, we don't have a number, we don't know how old it is exactly, but we have a much better range than just, well, it's younger than the layer it's on top of, right? We can actually now say, okay, well, it was at least in this few million years. It's not absolute dating because we're still comparing to something else, right? We're still using the fossil to say, oh, it compared to this fossil, it's older or younger, but we can put the range in much closer. Okay, so I'll show you what I mean with an example here. So if you just had the rock layers and no index fossils, all you would really be able to say is that this layer is the youngest, then this one, then this one, then this one, which is still true, but it's not that great, right? Yeah, okay, this layer is younger than that layer. Doesn't really give us even a close estimate of the age, right? However, ammonites, I see an ammonite here, they are an excellent index fossil. Okay, so I'll show you what I mean. So ammonites lived for a really short amount of time, okay? And they all went extinct about 65 million years ago. Okay, so if these guys went extinct 65 million years ago, and hey, we see them here and they didn't exist that long, well, guess what? What do we know now about every layer above here? That's right, we now know all of these layers are younger than 65 million years. See how we've kind of gotten a bit of a better estimate now? All we could say before was that these layers are younger than this layer, but maybe this layer is 100 million years and this, we don't know, right? It could be anything, it could be 1 billion years old. All we knew before we found this fossil was that these layers were younger. Now we can actually say, and on the flip side, now we can actually say all of these layers must be older than 65 million years. Not just must be older than this layer, we can actually start to put a bit of a number on it. Older than 65 million years. See, it's a little bit better, right? Okay, notice we're still saying older than, so we're still comparing, so this is still relative dating, but it's a lot better that we can say at least older than 65 million instead of just, oh, pretty old, right? The really interesting thing is that we can use these index fossils to do what's called correlation, okay, between two different areas. So now, even if the rock layers don't match up, the fossil record will match up, right? Because now in this other location, we have what's called correlation, and we can say, okay, well, these layers must be the same age. And we can also, even when the layers don't match up, it's okay because the fossil record will. So even though we're missing a layer here, usually because of erosion or something like that, we can use the index fossils to still kind of piece together a timeline here, right? So we might make the mistake of thinking this layer is not that much younger than this layer, but thanks to the fact that in other places we know there was millions of years where this thing existed, we can say, okay, there must just be a missing layer here. And we don't make the mistake of thinking these things came right after these things, right? Circling back to these big ideas that you've hopefully come away with. If not, just go back and see if you can find them, okay? What is relative dating? What is the law of superposition? Very important. Which strata, aka layers, are older? The lower ones are the higher ones. Okay, you should definitely be able to answer that. If an intrusion or a fault goes through a layer, is it older or younger than the layer? What is an index fossil? And how do index fossils improve the precision of our relative dating?